Hello, good morning, dear students. Welcome to Interactive Virtual Class Nagaland once again. So, students, we will continue with the same chapter, that is magnetic effects of electric current. So, let us see. Okay. So, here we see a needle is placed on this top. Right. Now, when we push the needle in this direction, okay, when we push the needle, it moves in this direction. Observe carefully. All right, students. Then next. Now when we push the needle towards this, the needle moves in this direction. Yes, students? So here, why is there a difference in the direction in which the needle moves? We see that in the first case, the needle moves in this direction. In the second case, the needle moves in this direction. So why is there a difference in the direction in which the needle moves? Yes, students? We see that in these two cases, the needles are moving in different direction. So why is it so? Do you have the answer? Yes, students? The needle moves in a direction in which the force is applied. Yes. So we push this needle in this direction. Yes. So we are applying force in this direction, and that is why this needle is moving towards this direction. In the second case, we push the needle in this direction. So we are applying force in this direction, and that is why the needle is moving in this direction in the second case. So the needle moves in a direction in which the force is applied. Now this applies to our everyday life as well, okay, to any other object. Place a pen or a book on your desk. All right, place a book or a pen on your desk and push the book, okay, and push the book towards your right. Then your book will move towards the direction in which you are applying force. Yes, students, it may not only be a book, it may be any other object, but the object will move in the direction in which we are applying force. Yes, students, so then here the needle moves in a direction in which its force is applied. Every object, okay, will moves in the direction in which force is applied when we push it. Yes, the object will move in a direction in which the force is applied. So remember this, okay? Object will move in the direction in which the force is applied. Now, do you know what will happen if we hang a current carrying conductor like this and pass current through it? Yes, students, in our previous class we have seen the different magnetic field lines produced by different shaped conductor. What if we take a straight current carrying conductor and hang it, okay, and allow current to pass through it? So let us see. So hang a current carrying conductor, okay. So hang this conductor, straight conductor, and allow current to pass through it. What do we see here? We did not observe any changes. Yes, students, we did not see any changes here. Now, what if we place this, okay, magnet here? What if we hang current carrying conductor in a magnetic field? Because when there is magnet, okay, when there is magnet, there will be magnetic field. Magnetic field will be produced. We can see here magnetic field lines are in the direction downward in this case, because the direction of magnetic field lines is from North Pole to South Pole. So here we have North Pole, we have South Pole. So the direction of magnetic field lines is downward in this case. So what will happen if we place, okay, or if we hang current carrying conductor in magnetic field? So observe carefully, okay. So when we allow current to pass through the conductor placed in magnetic field, what do we observe here? We see that this conductor is moving outward. Yes, students, we see that the conductor is moving outward. Do you agree? Yes, students. So we have two cases here. In the first case, conductor did not move. In the second case, conductor moved. The conductor is moving outward in this direction. So our question is, why did the current carrying conductor move? Yes, students, why did the current carrying conductor move? Now, if you can recall, we have just seen that the needle moves in the direction in which the force is applied. Yes, so here in the second case, the conductor must have experienced a force. Yes, because the object needs to experience a force in order to come in motion. So here the conductor move because this conductor must have experienced a force. So when did the current carrying conductor experience a force? In this case, the conductor did not move. So it means that this conductor did not experience force. But in this case, we see that the conductor moved outward. So we have seen that it must have experienced a force, right? So when did the current carrying conductor experience a force? So this conductor, in the presence of magnetic field, it experiences a force. Yes, students. So here, when the current carrying conductor is placed in magnetic field, it experiences a force, and that is why this conductor is in motion. It moves outward, whereas in this case, the conductor does not experience force because it is not in magnetic field. Okay, so the conductor does not move. So we have seen that this current carrying conductor, it moves outward because it experiences a force when it is placed in magnetic field. Now let us observe carefully. So when we pass current, okay, we see that the conductor move outward. Yes, the conductor move outward. Now let us take another case, okay, and reverse the direction of current. So when we reverse the direction of current, what do we observe? We see that the conductor moves in this direction. Now remember, students, in this case, the direction of magnetic field lines is the same. That is from North Pole to South Pole. So in both of this case, the direction of magnetic field line is downwards. Okay. Here we have reversed the direction of current. In this case, positive N is here, negative N is here. In this case, positive N is here, negative N is here. So that means the direction of current is from positive to negative. So it will go in this direction, the direction of current. In this case, the direction of current is from positive to negative. So the direction of current is in this direction. So here the direction of magnetic field is the same, but we have reversed the direction of current. So why is there a difference in the direction in which the conductor moves? Now in this case, we see that the conductor moves outward. In this case, the direction moves inward. So we see there is a difference in the direction in which the conductor moves, right? So why is it so? Yes, students, we see that when we reverse the direction of current, the direction in which the conductor moves also change. Yes, students. So in this case, the direction moves outward. In this case, the direction in which the conductor moves is outward in this case, and in this case, the direction in which the conductor moves is inward. So here we see that the current carrying conductor moves in a direction in which it experiences a force. Yes, so here this conductor is experiencing force in this direction, that is why it moves outward. In this case, the conductor experiences force in this direction, that is why it moves inward. Yes, students. So here, why is there a difference in the direction of force? In these two cases, we see that both the conductor are placed in magnetic field in the same direction. Yes, the magnetic field lines are in the same direction, but there is difference in direction of force. So why is there a difference in the direction of force? We see that there is difference in direction of current. So there is difference in direction of force in these two cases due to change in the direction of current. In these two cases, the direction of magnetic field lines is the same, but the direction of current is reverse. That is why when we change the direction of current, there will be difference in the direction of force. Now let us take this example. What will happen, okay, if we reverse the direction of magnetic field? So here the direction of magnetic field is upward, because the direction of magnetic field is always from North Pole to South Pole. So now what happens when we reverse this? Let us observe. When we reverse the direction of magnetic field, okay, and allow current to pass through the conductor, we see that this conductor moves inward. Yes, students, it is because the conductor experiences force in this direction. So we have two cases here. In this case, the direction of current is the same, okay, both the direction of current is in this direction, but we have reversed the direction of magnetic field. In this case it is downward, in this case it is upward. So what difference do we see here? Why is there a difference in the direction of force? In this case the conductor moves outward, in this case the direction moves inward. So why is there a difference in the direction of force in these two cases? We see that the direction of magnetic field lines is different in this case. So the direction of force, okay, there is a difference in the direction of force in these two cases due to change in the direction of magnetic field. Alright, so we have seen that the force direction, okay, or the direction of force changes due to change in the direction of current. In this case, the direction of magnetic field is the same. We have reversed the direction of current. Then we see the difference in which difference in the direction of force. The next is, again in these two cases, the direction of current is the same, but when we reverse the direction of magnetic field lines, then we see that there is direction in which there is difference in which this conductor move, right? The direction of this conductor is different. So there is difference, okay, in the direction of force. In this case it is outward, in this case it is inward. So here we see that the direction of force also changes due to change in the direction of magnetic field. So we can say that the direction of the force on the conductor depends upon the direction of current and direction of the magnetic field. Okay, remember this point, students. The direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. In order to change the direction of force, either the direction of current or the direction of magnetic field can be changed. So if we want to change the direction of force, we can do that either by changing the direction of current or by changing the direction of magnetic field. Is that clear to you, students? Alright. Now, what is the direction of force experienced by current carrying conductor placed in a magnetic field? Or, in other words, how do we determine the direction of force experienced by a current carrying conductor placed in a magnetic field? In our previous class, we have discussed about right-hand thumb rule. Yes, with the help of right-hand thumb rule, we were able to determine the direction of magnetic field lines. Yes, so how do we determine the direction of force experienced by current carrying conductor placed in magnetic field? So for this, we will use another rule known as Fleming's left-hand rule. Okay, Fleming's left-hand rule. So let us see here. So we have taken the first three fingers of our left hand. Okay, in this case, the forefinger, that is this finger, forefinger, will show the direction of magnetic field. Okay, it will show field direction. You can remember by this letter F. Okay, so this forefinger will show the direction of magnetic field. Middle finger is this finger. The middle finger will show the direction of current. Then we have the thumb. Okay, the thumb will show the direction of motion of conductor. Okay, motion of conductor, or in other words, force, direction of force, because the conductor will move in the direction of force. So thumb will determine, or thumb will show us the direction of force or direction of motion of conductor. Okay, so you can remember this by this letter M. All right. Now, what is Fleming's left hand rule? Okay, so for Fleming's left hand rule, hold the first three fingers of your left hand so that they are mutually perpendicular to each other. Okay, as shown here, hold the first three fingers of your left hand so that these three fingers are mutually perpendicular to each other. So this should be perpendicular to this finger, this should be perpendicular to this finger, and this thumb should be perpendicular to this middle finger. Okay, so here, according to Fleming's left hand rule, if the forefinger is in direction of magnetic field, middle finger indicates direction of current, and the thumb is in the direction of motion of conductor, or the thumb is in the direction of force. Okay, so using Fleming's left hand rule, we can determine the direction of current and direction of motion if we place the forefinger in the direction of magnetic field. All right. All right, students. So we have the first question for today. Please get your rough devices ready. The question is, the direction of the force on a current carrying conductor in a magnetic field depends on which of the following? Okay, I'm giving you 20 seconds for this question. Your time starts now. The direction of the force on a current carrying conductor in a magnetic field depends on option A, the magnitude of the current and length of the conductor. Option B, the direction of the current and direction of magnetic field. Option C, the material of the conductor. Option D, the resistance of the conductor. Alright students, your time is up, and yes, very good. We have seen that the direction of force on a current carrying conductor in magnetic field depends on the direction of current and direction of magnetic field. So the correct answer for this question is option B, that is the direction of the current and the magnetic field. So option B is the correct answer. Alright students, we have another question. Please get your rough devices ready. The question is, according to Fleming's left hand rule, the thumb represents the direction of which of the following? I'm giving you another 20 seconds for this question. Your time starts now. According to Fleming's left hand rule, the thumb represents the direction of, option A is magnetic field, option B is electric current, option C is force acting on the conductor, and option D is resistance of the conductor. So which of the following is the correct answer? Alright students, yes, very good. The correct answer for this question is option C, that is force acting on the conductor. According to Fleming's left hand rule, the thumb represents the direction of motion of the conductor or force acting on the conductor. So option C is the correct answer. Alright students, let us continue. Okay, so here we see a lady in a kitchen, right? So what is she doing? Let us see. So here she is using a grinder or a mixture, okay, to mix food or to grind food. So how does this grinder work? Yes students, if you have seen this, the grinder rotates, right, and it breaks the food substance into small pieces. So what is present inside this grinder and how does it work? Yes students, so there is a device called electric motor present inside this grinder. Okay, so we see here an electric motor. The next we see here is a boy entering a room to turn on the fan. Now on hot days, on sunny days, hot sunny days, when it is too hot, we turn on the fan, right? And the fan rotates. When the fan rotates, it keeps us cool, right? But how does this fan work? Okay, how does this fan rotate? What is present this fan? Okay, so in this fan as well, there is a device called electric motor is present. So what is this electric motor? Let us see. So an electric motor is a rotating device that converts electrical energy to mechanical energy. Okay, so in grinder, in fan, okay, there is this device called electric motor, and this electric motor is a rotating device. It converts electrical energy to mechanical energy. So this electric motor present inside fan is what makes the fan rotates. Okay, so let us see. Okay, let us learn about electric motor in today's class. So different parts of motor. What are the different parts of motor? So the first thing we observe here is that we see North Pole and South Pole, right? So when there is North Pole and South Pole, it means that there is magnet, right? So the first part of electric motor is magnet. The next part we see here is armature. Okay, so what is armature? So armature is a rectangular coil of insulated copper wire wound on a soft iron core. Okay, so the next part we have is armature. The next part we have is brushes. Okay, namely B1 and B2. So these are the two brushes present. Now these brushes are solid brushes. Okay, they are different from the usual brushes, but they are solid brushes. So these are the two brushes, namely B1 and B2. The next part of motor is split rings. Now if you observe carefully, we see that this is not a full ring, but we see two rings which are split into half, right? So we have split rings. Let's name them R1 and R2. Okay, let's name them R1 and R2. We have the electric cell and we have the switch. Yes, so we have magnet, armature, brushes and split rings in electric motor. These are the different parts of motor. Now in this case we see that B1, okay, brush B1 is connected to positive terminal of the battery. Okay, brush B1 is connected to positive terminal of the battery, and brush B2 is connected to negative terminal of the battery. Here this split ring R1 makes contact with the brush B1. Yes, R1 and B1 they make contact, and split ring R2 and brush B2 makes contact with each other. So R2 makes contact with the brush B2. Okay, so these are the different parts of motor. Now when we turn on the switch, we see that this armature is rotating, right? So how does it work? Let us see. Okay, so working of motor. How does this motor works? Let us see. Okay, so first, okay, we have this magnet. The direction of magnetic field is always from North Pole to South Pole. Yes, students, so this is the direction of magnetic field. Okay, this is the direction of magnetic field. So here we see from North Pole to South Pole. So the direction of magnetic field is in this direction. Now here we see that arms, okay, when we turn on the switch, the current flows from positive end to negative end, right? So the current flows in this direction. Okay, the current will flow in this direction. So here we see the flow of current. Now in this case, arm AD and BC are parallel to magnetic field lines. The direction of magnetic field lines is in this direction because it is from North Pole to South Pole. Arms AD and BC are also parallel to magnetic field lines because they are all in this direction. Yes, so arms AD and arms BC are parallel to magnetic field lines. In this case, we see that current flows in the direction DCBA. Electric current flows from positive end to negative end. So it starts from here, then it goes this direction. Yes, it goes this direction. So when we consider arms DC and BA, we see that the direction flows from DC in this direction and in this direction. Yes, students. So the current flows in a direction of DCBA. Now let us see. Okay, so when we look at this, we see that we have seen that arms AD and BC are parallel to magnetic field lines, but the direction of current, it is in this direction. The direction of magnetic field lines is in this direction. The direction of current is in this direction. So here we see that the magnetic field lines, okay, the direction of magnetic field lines is perpendicular to the direction of current. Okay, so direction of current is perpendicular to the direction of magnetic field lines. Now let us consider arm DC. Okay, we will look into it one by one. Okay, arm DC, arm BA. So first let us consider arm DC. So in arm DC, what is the direction of magnetic field? The direction of magnetic field is from north to south, so it will be in this direction. Yes, so the direction of magnetic field in arms DC is in this direction as shown here. Then what is the direction of current in arm DC? Current flows from positive end to negative end. So in DC the current is flowing in this direction. Yes, students. So here we see that direction of current is in this direction as shown here. Okay, the direction of current. So what will be the direction of force? Yes, what will be the direction of force in arm DC? According to Fleming's, okay, according to Fleming's left hand rule, we can see that the direction of force in arm DC is downward. Okay, the direction of force in arm DC is downward. Now the object moves in the direction of force, right? So arm DC will move downward. Okay, arms DC will move downward. Now let us consider arm BA. So what is the direction of magnetic field in arm BA? The direction of magnetic field line will be the same as DC. So the direction of magnetic field line as shown here is in this direction. What will be the direction of current in arm BA? The direction flows from positive end to negative end. So in DC it goes this direction, but in BA it will come in this direction. Yes, students. So the direction of current in BA is in this direction as shown. So what will be the direction of force in arm BA? Now using Fleming's left hand rule, we can see that the direction of force is upward. Remember, the object moves in direction of force. Arm BA, in arm DC, the direction of force is downward. In arm BA, the direction of force is upward. So this arm DC will move downward, arm BA will move upward. Okay, so let us see here the direction of force in arm DC and BA are opposite in direction. So the two forces are equal and opposite, which makes the coil rotate. Okay, so DC will move down and AB will move up. So when we turn on the current, we see that DC moves down because the direction of force in DC is downward. AB moves up because the direction of current in BA is upward. So here we see that the coil rotates. Yes, students. Now when this armature is in this position, okay, there is no contact between B1 and R1, B2 and R2. There is no contact between brush B1 and split ring R1. There is no contact between brush B2 and split ring R2 because there is some gap here. As you can see, there is some gap. So there is no contact between B1 and R1, B2 and R2. So here the brush is not in contact with the split ring, so the current to the coil is cut off. This split ring is not in contact with the brush, so the current is cut off because they are not in contact. So this coil, okay, this armature will experience no force. Okay, in this position this armature will experience no force. So thus the coil stop in this position. Will this coil stop rotating in this position? No, right? It keeps rotating. So the coil does not stop and continues in its motion due to its inertia of motion. Okay, so in this position, the coil does not experience force because the current, okay, is disconnected. There is no connection between this brush and ring, so the current does not flow. But this coil does not stop rotating, but it continues to its motion due to inertia of motion. Now, what is inertia of motion? Inertia of motion is the tendency of an object to remain in motion. So because of its inertia of motion, this coil continues to rotate. Now when it rotates, okay, it will come to this position. Now they have exchange. Arm BA is here now, arm DC is here. Now in this case, we see that B1 is in contact with R2 and B2 is in contact with R1. Yes, students. So here R1 makes contact with brush B2 and split ring R2 makes contact with brush B1. So they have reversed the position. Now let us see again here. But the direction of current is the same because we have not changed the connection of current. Now, current, in this case, current flows in the direction of A, B, C, D now. In the first case, direction of current was from D, C, B, A, right? But now the direction of current is from A, B, C, D, okay? Now, let us consider arm AB, okay? Let us consider arm AB. So, what is the direction of magnetic field in arm AB? The direction of magnetic field remains the same because it is from North Pole to South Pole. So the direction of magnetic field in arm AB is in this direction as shown. Then direction of current in arm AB is, let us observe the direction in which the current is flowing. So we observe that the direction of current is in this direction. Now what will be the direction of force in this case? Remember, these three arms, okay, these three direction, that is direction of force, direction of magnetic field and direction of current should be mutually perpendicular to each other. So we can, using Fleming's left hand rule, again we see that the direction of force is downward in arm AB. Okay, so the direction of force in arm AB is downward. Similarly, consider arm CD. The direction of magnetic field in arm CD will be in this direction from North Pole to South Pole. The direction of current will be in this direction. Yes, because the current is coming from A, B, C, D, right? What will be the direction of force in arm CD? So the direction of force in arm CD is upward. Remember again, the object moves in the direction of force. So in this case, okay, in arm AB, the direction of force is downward, and in arm CD, the direction of force is upward. So this AB will move downward, CD will move upward. So let us observe. Okay. So here these two forces are equal and opposite, which makes the coil rotate. So again, in this case, AB will move downward, CD will move upward. Okay. So here, this is how, okay, the motor works. AB moves downwards, CD moves upwards. So this is first half rotation. Okay, we have the first half rotation and we have the second half rotation. In first half rotation, DC moves downwards, AB, okay, BA moves upwards. In the second half rotation, AB moves downwards and CD move upwards. So we have first half rotation and second half rotation. Alright, students. So here we see that the direction of current in the coil reverses for every half rotation. The direction of current in the coil reverses for every half rotation. A device that reverses the direction of flow of current through a circuit is called a commutator. Okay, and in electric motors, the split rings at acts as a commutator. Okay, so here DC goes down, BA goes up. In second half rotation, AB goes down and CD goes up. So this is how the coils continues to rotate. The reversal of current also reverses the direction of force acting on two arms AB and CD. So the coil continues to rotate in the same direction. Okay, the coil continue to rotate in the same direction as there is reversal of current after every first half rotation. So let us observe. Okay, we have the armature, we have the direction of magnetic field. So this is plane of coil. This is the direction of magnetic field, and this is the plane of coil, right? So when plane of coil is parallel, okay, to direction of magnetic field, this is the position where this armature it will experience maximum force. When this plane of coil is parallel to the direction of magnetic field, it will experience maximum force. Now when it rotates, this is first half rotation, right? So here we see that the plane of coil is perpendicular to direction of magnetic field, right? So here plane of coil is perpendicular to direction of magnetic field. So when this plane of coil is perpendicular, it will experience minimum force or it will experience zero force. Alright students, we have another question. Please get your rough devices ready. The question is, an electric motor converts which of the following? Okay, I'm giving you 15 seconds for this question. Your time starts now. So an electric motor converts, option A, electrical energy to mechanical energy, mechanical energy to electrical energy, electrical energy to magnetic energy, mechanical energy to magnetic energy. Alright students, yes, very good. The correct answer for this question is option A, that is an electric motor converts electrical energy to mechanical energy. Alright students, we have another question. Please get your rough devices ready. The question is, in which of the following devices, okay. Alright students, before this let us discuss, okay, one more thing. So here we see, okay, these are some of the practical examples of electric motors. This electric motor is also used inside PC, okay, or computer. It is also used in refrigerator. It is also used in dryer, okay, in motor, okay, electric motor. So these are some of the practical uses of electric motor. So here we have electric motor. The commercial motors, okay, the commercial motors, it uses an electromagnet in place of permanent magnet. It uses large number of turns of conducting wire in the current carrying coil and a soft iron core on which the coil is wound. So these are some of the parts present inside the electric motor. Okay. Alright students, we have another question. Please get your rough devices ready and respond to this question. In which of the following devices are electric motors commonly used? So I'm giving you 15 seconds to respond to this question. Your time starts now. In which of the following devices are electric motors commonly used? Solar panels, electric fans, chemical batteries, light bulbs. Alright students, your time is up, and yes, very good. The correct answer for this question is option B, that is electric fans. Alright students, we have another question. The question is, the working of an electric motor is based on which of the following? Okay, I'm giving you 20 seconds for this question. Your time starts now. The working of an electric motor is based on heating effect of electric current, chemical effect of electric current, magnetic effect of electric current, and electrostatic effect of electric current. Yes, students? Alright students, your time is up, and yes, very good. The correct answer is option C, that is magnetic effect of electric current. Alright students, so in today's class we have discussed about, okay, that the direction of force of conductor placed in magnetic field depends on the direction of current and direction of magnetic field. We can determine the direction of force on the conductor placed in magnetic field by using Fleming's left hand rule. We have also discussed about electric motors, right? We have seen the different parts of electric motor. We have also seen the working, how electric motor works, and we have also seen discussed some of the uses of electric motors. So these are some of the things that we have discussed today. I hope you are clear with what we have discussed in today's class. Yes students, so this is all for today's class. Thank you so much for joining today's class. I will see you again in our next class. Till then, take care everyone and have a nice day.